Hello everyone, so today's lesson we're going to go over how to find y-intercepts, specifically of polynomials, and then we're going to talk about complex conjugates, imaginary roots, and a bunch of other cool stuff. All right, so for the first one it says find the y-coordinate of the y-intercept of the polynomial function defined below. Now, this doesn't just go for polynomials, this goes for any function in general. If you're trying to find the y-intercept, you plug in, your y-intercept is going to be 0, comma something. So if you plug in 0 for x, you know that you're automatically going to find the y-intercept, okay? So what we can do is we can go ahead and we're just going to plug in 0 for x. So we're going to do negative 2 times 0 squared plus 3 times 2 times 0 minus 4 times 3 times 0 plus 1 squared. All right, so literally all I did is wherever I see an x in here, I'm plugging in a 0. So I'm going to do negative 2 times 0 squared plus 3 times 2 times 0 minus 4 times 3 times 0 plus 1. Make sure I didn't mess up there. And then we got to square this. All right, and I got 216. So that means that the y-intercept would be 0, comma 216. But specifically to answer the question, they just want the y-coordinate of the y-intercept. So the answer would be 216. All right. So again, to find the y-intercept, you simply plug in 0 for x. Now, it says, what's the conjugate? So we learned in math 2 that for conjugates, essentially what you do is you switch the sign in front of the complex part. So the complex part here is 6i. So the conjugate here is going to be negative 8 plus 6i. You don't switch the sign in front of the real part. You switch the sign in front of the complex part. So the conjugate here is going to be plus 6i. All right. Next, it says which quadratic equation has roots 8 plus 6i and 8 minus 6i. So first off, I want to point out that these right here are complex conjugates of each other, right? The real part is 8 and the imaginary part is the 6i, and we switch the sign in front of the 6i. So I just want to point out that these two are complex conjugates of each other. And basically what they're doing here is they're giving us the roots, and they want us to work backwards and find the quadratic that came from. You know how like when you use the quadratic formula and you get two imaginary solutions, you should be able to work backwards using those solutions to find the original quadratic. So basically, if these are the roots, we know that with polynomials or quadratics or whatever, it's always x minus the root. So that's what we're going to do here. We're going to do x minus 8 plus 6i times x minus 8 minus 6i. All right. And what we can do is we can distribute that. We get x minus 8 minus 6i, x minus 8 plus 6i. All I did was distribute this negative, distribute this negative. All right, so now what we have to do is we just have to multiply all these terms. So we're going to go ahead and distribute this x to everything. We get x squared minus 8x plus 6xi. Then we'll go ahead and distribute this negative 8. So we get minus 8x plus 64 minus 48i. Then we go ahead and we can distribute, I don't want to use red, this negative 6i. So we end up with minus 6xi plus 48i minus 36i squared. All right. So what you're going to notice when you do these is that a lot of the terms are going to cancel out. This guy cancels with this guy, and this guy cancels with this guy. Essentially, all of the things with I should go away. All right. Then the other thing is last year we learned that I squared is equal to -1. So anything with an I squared in there, we can replace that with a -1. So basically we're going to end up with x squared, and we can combine like terms here. We get minus 16i, not 16i, I'm sorry, minus 16x. We got plus 64, and this ends up being minus 36 times -1, which negative 36 times -1 is going to be a positive 36. So then we could just go ahead, combine like terms there. Let's see, 64 and 100. Let's see. Yes, we get 100. All right, so then we can go ahead and look which one of these quadratics perfectly matches with what we got, and it's going to be this guy right here. All right, so essentially what you're doing is, just to recap, you take the root, you do x minus the roots, multiply it out, and you're able to get the quadratic equation. All right. All right, so now this is the same thing, except for it's not multiple choice, and they actually gave us real roots, which makes things a little bit easier. So if the root is -6 and -7, we know that the way that it's written is it's like x minus the root. So the signs flip. So we would end up with like x minus -7 and x minus -6, which gives us x plus 7, x plus 6. Then we just simply FOIL this out. All right. We get x squared plus 6x plus 7x plus 42, which gives us x squared plus 13x plus 42. All right. So that gives us our answer there. Now this next one is just like the first one we did here, where it's imaginary roots that we're starting out with, and they're asking us to provide the quadratic equation that those roots came from. So again, it would be x minus my roots, which is minus 9 plus 3i, x minus -9 minus 3i. And notice these guys are two roots. They're just written as plus minus. They're complex conjugates of each other, right? We got -9 plus 3i, -9 minus 3i. They are conjugates because we've got the plus and minus in front of that imaginary part. So we could go ahead, distribute the negative to these guys. So we end up with x plus 9 minus 3i, x plus 9 plus 3i. All right, and then we got to go ahead and multiply this out. Again, is it a little bit ugly? Yes, but we can handle it. We get, excuse me, we get x squared plus 9x plus 3xi. And then we'll go ahead and distribute this 9, and we get plus 9x. Gee, excuse me. Plus 81, plus 27i. And then we're going to go ahead and distribute this -3i. So we get minus 3xi minus 27i minus 9i squared. So this is the point where a lot of stuff's supposed to cancel. Hopefully it will, right? My 3xi is going to cancel with my -3xi. My 27i is going to cancel with my -27i. And then I have to replace this I squared here with a -1. So if I have -9 times -1, that's going to end up becoming a plus 9. So we go ahead. We're left with x squared plus 9x plus 9x plus 81 plus 9. And you can just combine all your like terms. X squared plus 18x plus 90. And that is our starting quadratic there. That is what we would plug in. So yeah. All right. Next one here. So now, in this case, they gave us real roots. However, they are irrational. That means, you know, when you simplify the radical, you still have something inside of the radical, which is totally doable, right? Again, we're going to follow the idea that we do x minus the roots, right? So we're going to do x minus, and then we've got 8 plus root 15, x minus 8 minus root 15. All right, so we distribute that negative And we end up with x minus 8 minus root 15 times x minus 8 plus root 15. And we have to go ahead and distribute. We get x squared minus 8x plus root 15x, or x root 15. I guess it might be a little nicer to put the x in front of the root. It doesn't really matter, though. All right, and then we're going to go ahead and distribute the negative 8. So we get minus 8x plus 64 minus 8 root 15. And we've got to distribute our negative root 15, which is going to give us a minus x root 15 plus 8 root 15. And then it's going to be minus root. And then when you multiply things that are both in the radical, you multiply the stuff inside of the radical. So 15 times 15 is 225. All right. So just like the imaginary solutions, stuff should cancel here. So we look, and this x root 15 cancels with the negative x root 15. The 8 root 15 cancels, or the negative 8 root 15 cancels with the 8 root 15. And the square root of 225 is 15. So we should end up with a minus 15 there. So we can go ahead and rewrite this as x squared minus 8x plus 64 minus 15. So our final answer should be x squared minus 16x, and then 64 minus 15 gives us 49. What the heck? Plus 49. All right, so that would be our answer there.